Hello everyone, my name is Junya Shijubo. I'm a student in the Graduate School of Informatics, Kyoto University. I'm going to present our work which optimizes black box checking, and this is a joint work with Masaki, Waga, and Kohei Suenaga. They are my supervisors. Black box checking is a testing method. It combines model checking and automata learning, and we optimize it by model checking with strengthened specification. Cyber-physical systems such as robots and automobiles are widely used in the world. CPS is implemented as a combination of software and physical mechanisms. Since CPS has physical mechanisms, and its unexpected behavior may harm humans. Due to its safety-critical nature, safety assurance of CPS is critical. So we need a method to verify its behavior. A CPS tends to be a black box system because usually CPS is a highly complicated system and model construction of CPS is hard. And some components may be third-party products and we can't know its internals. Therefore, we need a black box testing method for CPS. As a naive testing method for black box systems, there is random testing. In random testing, first, the verifier randomly generates many inputs, and then the verifier feeds the inputs to the black box system M and observes the outputs, and check if outputs satisfy the specification. As a more sophisticated testing method for black box systems, there is black box checking, which we call BBC in this presentation. BBC is a testing method that combines automata learning and model checking. First, using automata learning, BBC constructs an automaton M-childer that approximates the behavior of system M. Then, using model checking, BBC judges if the automaton satisfies the specification or not. This figure shows the detailed workflow of BBC. BBC is given the system M and the specification phi as input. Initially, BBC learns the automaton M-childer that approximates the behavior of system M. Notice at this point, the learned M-childer may not be equivalent to system M. In order to refine the learning of automaton, we need an input that shows the difference between system and automaton. BBC finds such an input in the following way. First, model check the learned automaton satisfies the specification. If the automaton violates the specification, a witness sigma of violation is found. BBC then feeds this sigma to the original system M and observes its behavior, and check if the system M violates the specification for input sigma. If the system violates the specification, then BBC returns M not models phi with a counterexample sigma. If the system M satisfies the specification for input sigma, then this sigma is an input that exhibits the difference between a system M and automaton M-childer. Then BBC uses this sigma as a new input to the automata learning procedure to obtain new automaton. And in the model checking steps, if the automaton satisfies the specification, then BBC executes the equivalence testing. If equivalence testing discovers an input sigma that exhibits the difference between M and M-childer, BBC uses this sigma to refine the automaton. Otherwise, BBC deems system M and automaton M-childer are equivalent and returns M models phi. One of the practical issues in BBC for CPS is its long execution time. The bottleneck is equivalence testing, because it typically finds a counterexample by generating many inputs and executing system M and automaton M children many times. Especially for CPS, its execution takes a long time due to its complexity. Our observation of BBC is as follows. We have two loops for finding an input to refine the automaton M children. The loop on the left executes an equivalence testing procedure that takes a long time. The loop on the right just executes the system M in this step, and the right loop is more efficient than the left one. Our solution is here. The red box is our modification. We strengthen the original specification phi to phi prime in this step, and model check the automaton against the strengthened specification phi prime in this step. The strengthened phi prime is easier to refute for model checker. If we cannot find a witness sigma in the model checking with original specification in this step, we have more chance to get the witness sigma by adding this step of model checking with strengthened specification. And if we get the witness sigma, then goes to right, and in this step, we run the system with input sigma and observe its behavior. If system satisfies the specification, then this sigma exhibits the difference of M and M children and use this sigma to define the automaton. On the other hand, if system violates the phi prime, then this phi prime is useless and BBC executes the equivalence testing. By adding this red-light loop, we can reduce the number of equivalence testing. This is more efficient than the original BBC. Our contributions are as follows. We introduced syntactic strengthening rules for LTL formulas. In our method, we allow intervals of temporal operators in LTL. This is not standard LTL, but this does not change the expressive power of LTL. Second, we proposed optimized BBC via model checking with strengthened specification. Third, we conducted experiments and evaluated them. Our results shows up to 66% faster than the original BBC. Next, I explain about syntactic strengthening rules. Syntactic means the rules rewrite logical operators of LTL formulas or change intervals of temporal operators. To formalize the strengthening rules, we define the strengthening relation phi right arrow psi. Phi means the original specification and psi means strengthened specification. And we prove the correctness of strengthening relation. And this theorem means phi right arrow psi essentially means psi is stronger than phi. This is a definition of strengthening relation. I explain some of these using examples. This is an example of strengthening by rewriting logical operators. Let the example specification eventually P1 or eventually 0 to 10 P2. The rule 1 means rewriting logical OR to logical AND. So we rewrite OR operator of original specification to AND operator, and we have this strengthened specification. Here is another example of rewriting logical operators. The rules allow to rewrite eventually to global eventually eventually globally or globally. This is because these four LTL formulas means like these, and we can find the order of strengths. The weakest at the top and the strongest at the bottom. So we rewrite eventually P1 of original specification to globally eventually or eventually globally or globally. Then we have these strengths in the specifications. This is an example of strengthening by changing interval of temporal operators. The rule 7 allows to reduce interval of eventually operator. So we reduce the interval 0 to 10 to 0 to 5, and we have this strength in the specification. Notice that in this example, we can use any interval that is narrower than 0 to 10, and we can generate many strengths in the specifications. Next, I talk about BBC with strengths and specifications. To use strengths and specifications in model checking step of BBC, we need to choose strengths and specifications. In optimization of BBC, we model check with a strength and specification 5'. For this 5', when 5' is too strong, the witness sigma of violation on automata M tilde is also a witness of violation on system M. In this case, we cannot use sigma to define automaton M tilde. On the other hand, when 5' is too weak, this 5' is almost equal to original phi, and automaton M tilde often satisfies 5', and we cannot get the witness sigma. So we need an appropriate strengthening. I explain our design choice of choosing strengths and specifications. We divide the ways of choosing into two cases. First case is choosing spec strengthening by changing intervals. The second case is choosing spec strengthening by rewriting logical operators. When we choose specifications strengthened by changing intervals, we change the intervals as follows. Assume that we strengthen globally 0 to 22p. This line means interval 0 to 22. First, we choose interval 0 to infinity. And globally 0 to infinity p is equal to globally p, and this is the strongest specification. And then in BBC, if the system violates this 0 to infinity specification, then we choose the interval 0 to 30. This is weaker than 0 to infinity, and upper bound 30 is our choice in experiments, which is upper bound of the length of inputs. Then in BBC, if the system violates this 0 to 30 specification, then we choose the interval 0 to 26. We calculate 26 from the midpoint of 22 and 30. 22 is the upper bound of original specification, and 30 is the upper bound of current violated specification. And similarly, if system violates the specification with interval 0 to 26, then we choose the interval 0 to 24. And if the system violates 0 to 24, then we choose 0 to 23. When we choose a specification strengthened by writing logical operators, we rewrite all the logical operators that we can strengthen, and then we choose the strongest one. For example, assume that we strengthen this specification phi. We rewrite any logical operator that we can strengthen. In this case, this OR operator and this eventually operator, and we get the set phi operator of strength and specification. And we choose the strongest one from phi operator. In this case, the first specification is the strongest, and in BBC, the system violates this specification. Then we choose the next one, and then third one, and fourth one. Finally, I talk about experiments. As a baseline, we use Falcon, which executes BBC for CPSs. And we implemented our method as a prototype tool based on Falcon. And we measure the execution time 50 times for each method. Benchmark is here. As a system, we use Simulink model of an automatic transition system. And we used these 5 specifications. And some of these are taken from Zhang et al. 2018. These figures show experiment result. The left figure is average execution time of 50 runs. And for 5.4, our method is 66% faster than the baseline. For other specifications, our method is also faster. The right figure shows the number of timeouts of 50 runs. For 5.1 and for 5.4 and 5.5, both our method and the baseline didn't reach timeout. For 5.2, our method reduces timeouts. This is desirable. And for 5.3, the number of timeouts are the same. For specification 5.1 and 2 and 4, acceleration by our method was about 27% to 66%. Our method generates many strengthened specifications by changing the interval of temporal operators, such as 0 to 26 or 28 to 28. And model checking with them guided automata learning in BBC. For specification 5.3 and 5.5, our method was only 5% faster than baseline. For 5.3, most strengthened specifications are also difficult. This is because falsification of a disjunctive specification tends to be difficult, and our strengthened specification also disjunctive ones. So improvements by model checking with them are limited. For 5.5, the original specification is not difficult, so we cannot ignore the overhead of model checking with strengthened specifications. So to conclude, we optimized BBC with strengthened specifications. In optimization, we model check with strengthened specifications, and which reduces the number of equivalence tests. And our experiment shows our method accelerates BBC, and our method is up to 66% faster than the original BBC. As a future work, when the original specification contains many operators, optimization of the choice of the strengthened operator is future work. And investigation of other kinds of specification strengthening is also future work. And that's it. Thank you for listening.